So, welcome you guys. Hope you are doing well with the previous lectures. And today we are going to discuss about one of the most important topic of the atomic structure chapter. Here you will get a very to the point and prompt idea of the Planck's quantum theory, Bohr's atomic model and all of its applications type wise. And lastly, we will discuss every type of numericals and also the previous year questions. And with all this, I can guarantee that you are going to face 1 to 3 questions from this video directly in your NEET or AIIMS question paper. So guys, don't waste any more time. Be focused and let's move to today's topic. Here we are going to talk about the Planck's quantum theory. So, Planck's quantum theory is for any type of moving body or moving particle. That is what he told. He told that any particle in motion either radiates energy or absorbs energy. And with this idea, he also included that the emission of energy or absorption of energy is not discontinuous. It is a continuous process rather. So, Planck's quantum theory for any moving body or moving particle. Number 1, there is either absorption of energy or radiation of energy, and it is a continuous process. Now, how does the energy is absorbed or radiated? Here, Planck has given us a new term, that is quantum. He told that the energy is absorbed or radiated in the form of quantum. Quantum is small and discrete packets of energy. So, the energy is absorbed or radiated in the form of small discrete packets, and those packets are called quantum. Let us take an example. For light energy, the quantum is photon. So, in the form of photon, light is absorbed or radiated. Okay, nextly, Planck has also given us the relation in between the energy in each quantum and the frequency of radiation or absorption. This is the most important concept of Planck's quantum theory. He gave us the concept of quantum and he also gave us the relation. He told that energy in each quantum is directly proportional to the frequency of radiation or absorption of energy. Now, what does this actually mean? Let us take that energy in each quantum be E and frequency of radiation be nu. Now, according to Planck's theory, E is directly proportional to nu, and from here we can get E equal to h nu. Now here you see h is nothing but the Planck's constant. So it is the famous Planck's constant h, and its value is h equal to 6.626 into 10 to the power minus 31 kilojoule second. So here we get the Planck's constant and the relation is E equal to h nu, where h is the Planck's constant and its values are, this is the CGS value. Remember the unit kilojoule second, and in CGS it will be 6.626 into 10 to the power minus 27 arc second. So So this is the Planck's constant and here is the relation. Remember this for numerical purpose. Now you see another relations from this concept and all these are very important for numerical purpose. See, here E is the energy of each quantum. Now let us assume that the total energy for a large number of quantum be E, let's for n number of quanta. Okay, now according to this Planck's concept, we get that E equals to n into h nu, that is for each quantum E equals to h nu, and here we have considered this capital E for n number of quanta. So capital E is equal to n h mu, and here you see again we know that mu is equals to c by lambda, where c is equals to the velocity of light and lambda is the wavelength of radiation. So putting the value of mu, we get nhc by lambda. This is another very important relation for energy E is equals to n number of quantum into h Planck's constant, c speed of light, and lambda, that is wavelength of radiation. And from this we again get that E is equals to nhc mu bar. Now what is this mu bar? Mu bar is nothing but 1 by lambda. So mu bar is the representation of 1 by lambda. Remember this relation also for your MCQ purpose. So here we have got three relations from the Planck's quantum theory, and all these three, this is number 1, this is number 2, and this is number 3. All these three relations you will be getting in the numerical section while I will solve those previous year questions. Okay, so please remember all these three relations for Planck's quantum theory. Hope you have understood this well. Now we will move to the Bohr's concept. Okay, Bohr's model and Bohr's concept. We will also correlate the Planck's quantum theory along with the Bohr's concept. Please watch till end, and the numericals of this section you will get in separate video because this video is going to be so long. So I will make a separate video for these numerical concepts, and you can get the numerical section from the I button above. Okay, so now let's go to the Bohr's concept. Now we have come to the Bohr's atomic model. First and foremost, remember that this model, that is Bohr's atomic model, is only for single electron species. That is, this model is only applicable, or these ideas of Bohr is only applicable for single electron species. Remember this. Okay, so what is actually single electron species? Let us take some examples like hydrogen atom. Next, helium plus atom. What does this mean? In natural helium atom or neutral helium atom, we know helium consists of 2 electrons, and here you can see a positive side, and it means one of the 2 electrons has gone away from its orbit, so it has left 1 electron. So helium plus atom is also a single electron species. Nextly, let us take lithium 2 plus. It means 2 electrons have gone away. We know lithium has 3 electrons neutrally and 2 has gone. So lithium 2 plus is also a single electron species. So remember, Bohr's model only applicable for this kind of single electron species. Now nextly, this Bohr's model is dependent on the particle nature of electrons. So, the Bohr's atomic model does not give any idea of any wave nature or electromagnetic nature. Rather, it just gives the idea of the particle nature of electrons. And thirdly, what Bohr told, that the negatively charged electrons is moving around the positively charged nucleus just like the planets are moving around the sun. And he told that the forces are just balanced, that is the attraction force of nucleus and electron and the centrifugal force which drives away the electrons from its orbit are just balanced, so that the electrons are moving in a specified orbit. And what more he has told? He has told that electrons are moving in stationary and circular orbit. So he has given a particular shape to the orbit of the electrons, and also he told that orbits are stationary in nature. And fourthly, he told that these stationary orbits, electrons moving in these stationary orbits has a constant energy level. He also concluded this. Bohr did not tell that the electrons can move in any orbit. Rather, he specified orbit. Let's see how he specified the orbits for any specific electron. Electrons can only revolve. That is, electrons can only move. That is, in the orbits which have angular momentum of electron is any integral multiple of h by 2 pi. So, in this way, Bohr just specified the orbit for any specific electron. Let's see what this idea, according to this, the angular momentum of any electron, let's be mvr, where m is the mass of electron, v is the velocity at which the electron is moving within the orbit, and r is the radius of the orbit. And this radius is specified, mvr, that is angular momentum, is equal to any integral multiple. Let's n be any integer, that is n into h by 2 pi, where n is any integer. So this gives the idea of Bohr's atomic model and Bohr's concept of stationary specified orbits. Here we have got mvr equal to nh by 2 pi. N is any integer, that is 1, 2, 3, dot dot, and h, you know now, that is Planck's constant, and it has a specific value, and pi is another constant value. And from this you can see n is any integer, h and 2 pi, this is a constant value. That means any electron moving in any specific orbit, that is n, has a specific and fixed angular momentum. From this idea you can conclude that, and you can see the angular momentum of any electron can have values like h by 2 pi, 2h by 2 pi, 3h by 2 pi, 7h by 2 pi, any integer at the place of n. But it cannot have in fractional values like 1 h by 2 pi, like 2.4 h by 2 pi, these values are possible for angular momentum of any electron, but these fractional values are not possible for angular momentum of electron. So please get the idea in your mind. Theoretical question may come from this specific idea. Okay, now we will see what more we can dig into the Bohr's atomic model. So now you see, this is the part of the atom. Okay, here you have got the nucleus and here you have got the definite orbits around the nucleus. And from the previous discussions, you have already known that this orbits has specific and different energy levels, and let those different energy levels be E1, E2, E3, E4 and E5. And accordingly, those orbits have got its specific name. And now see, MVR equal to NH by 2 pi. And for n equal to 1, that is for the first orbit nearest to the nucleus, we have got its name as K shell. And for n equal to 2, we have got L shell. N equal to 3 is M shell. N equal to 4 is N shell. And n equal to 5 is O shell. Just like that, the orbits are accordingly named. And this K shell, L shell, M, N, O shell has different energy levels. And here you can see the K shell. The K shell has the lowest energy level and the O shell has the highest energy level. And electrons within the K shell accordingly has the lowest energy, and electrons of this L, M, N shell has respectively greater energy level than the previous one. And when any electron within these orbits absorbs or maybe emits energy, then those electrons just jump from one orbit to the another. If any electron absorbs some energy, its energy level is increased. So it jumps from a nearest orbit to a far orbit from the nucleus. Whereas if any electron just emits energy from it, that means its energy level is decreased and it just jumps to a nearest orbit to the nucleus. So please remember all this concept, and this concept will be very valuable for solving the numericals that I will come just later on. Now we will see some applications regarding the Bohr's atomic model. We will not go to the derivation of the applications because those are just useless. We will just take the fruits from those huge trees. Okay, so let's go to the applications. So now we will just divide the applications of Bohr's atomic model into 3 parts. Firstly, we will see for the radius of a specific orbit. Nextly, we will see the velocity of an electron. Velocity of an electron within the specific orbit. And thirdly, we will see the energy of the electron within any of those orbits. So the application is just consists of these 3 ideas. So let's start with the radius of Bohr's orbit. Let's start with this. Here we will just go through a huge formula. No derivation is needed. You just see the formula at first. So radius of Bohr's orbit. Let the radius be r. That is equal to n square h square divided by 4 pi square m k z e square. So here you have got the radius of Bohr orbit's formula. This is a huge formula, you can see. Now you have to know the actual use of this formula. Here you see r is the radius of the orbit, and n, you know, n is any integer, and h, you know, the Planck's constant. 4 pi square is another constant, and this m here is the mass of the electron moving within the orbit, and k is another constant value, and z is the atomic number of the specific atoms which radius of orbit we need to know, and E is nothing but the amount of charge of electrons in the orbit. And you see, from the term z square we will just get the total amount of charge present in the orbit. Now you see what you actually needed from this formula. Okay, you see, radius of any orbit is just directly proportional to n square, and here n denotes the shell or the orbit for which we are calculating the radius. So for k shell, n is 1, l shell, n is 2, m shell, n is 3, just like that. So radius is directly proportional to n square, and here you can see h square is constant, and similar in case of 4 pi square, it is an also constant value. Now you see, radius is inversely proportional to the mass of the electron. You can see that. Okay, and nextly you see this z, that is radius, is also inversely proportional to z, and z is the atomic number, and here is left E square, which is also a constant value. Okay, so you need to remember these three only, that is radius is directly proportional to the n square value, inversely proportional to mass of electron, and also inversely proportional to the atomic number of the electron. And now if we put this whole idea for a single electron species like hydrogen atom, helium plus atom, lithium 2 plus atom, what we will get? We will get radius equal to 0.529 into n square by z Armstrong. Putting all the values for h square, 4 pi square, m, k and e square for a single electron species, we will just come into this conclusion, that is r radius equal to 0.529 into n square divided by the atomic number. And here you must note the unit, that is Armstrong, that is 10 to the power minus 10 meter. Okay, please remember this concept. Okay, so this is the whole idea for the radius of Bohr's orbit. You need to remember these three relations, and lastly you need to remember this relation for single electron species. Okay, so now we will just move to our first one is completed. Now we will move to velocity of an electron. So velocity of an electron, let given by v equal to 2 pi k z square divided by nh. So this is the formula for velocity of any electron moving in a specific orbit. From here we can see that v is the velocity of electron. Here 2 pi k e square and h is constant value, and what is left, that is v is directly proportional to z and v is inversely proportional to n. This two relation, what does this mean? Velocity of an electron is directly proportional to the atomic number of the atom, and velocity of electron is inversely proportional to the specific shell or orbit. That is value of n for k shell, you know, that is 1, for L shell that is 2, for M shell that is 3. So these two relations you need to remember, just like that of for the radius of an atom. Okay, and now we will again see the value of this velocity for single electron species. After putting all the constant values of these 2 pi k, e square and h, we have got that for single electron species, velocity of electron 2.18 into 10 to the power 6 z by n, and here you must note the unit, that is meter per second. So here is the value of velocity for any single electron species. Remember this unit here. So this and this relations are going to be actually needed for your numerical purpose. And just at the end of this theory part, we will see how these actually work for the numericals. Now we will come to the energy of an electron. And here you will see this is the most important application for Bohr's theory. So energy of the electron, you need to focus a little bit more. So let's go to the energy. So here we will see for the energy of an electron in any orbit. So we know energy has many forms. Here we will just discuss about two formats. That is the potential energy of electron and the kinetic energy of electron. And with these two, we will just calculate for the total energy of the electron. So see very carefully. Remember, potential energy is always negative for any electron, whereas the kinetic energy is positive always. And with these two, the total energy of the electron must be negative always. Remember this idea in your mind. Now we will come to the value of the potential energy. Here, after huge derivation, the potential energy comes to be k z e square by r, where k is any constant value, z is the atomic number, e square is the charge, and r is the radius of the orbit in which the electron is moving. And we know potential energy is always negative, so a minus sign just before this value. Similarly, kinetic energy is positive in nature, and k z square by 2r. And after summation of these two, we have got the total energy, that is also negative, and the value is k z square by 2r. Now you see the potential energy is inversely proportional to the negative value of the radius, whereas the kinetic energy is inversely proportional to the positive value of twice of the radius, and the total energy is also inversely proportional to the negative value of twice of the value of radius. So this is actually what we have to learn from this idea of the energy of electron. You just remember these relations and you will get the numericals to be very easy. Now see again, with these relations we can conclude that if the radius increases, the potential energy also increases. See, here we have got a negative sign. So here if the radius increases, then the potential energy also increases. And again if the radius increases, the kinetic energy decreases because here is the positive sign is present, and if radius increases, the total energy of the electron also increases because of this negative sign. So please remember these three relations along with these three. Now, after this much discussion, you see an amazing relation. The relation between potential energy, kinetic energy and the total energy. We can see that the total energy and the kinetic energy are numerically same. Both are kz square by 2r. But the difference is in their sign. Kinetic energy is just positive and total energy is just negative. So here we draw a relation between the kinetic energy and the total energy. That is, kinetic energy is equals to negative of total energy of an electron. Their numerical value are just same. Now we will relate the total energy with the potential energy. Here you see both are minus, both are negative value, but here we have got an extra half. So the total energy of an electron is just half that of the potential energy of the electron. So we have got the potential energy is equals to twice the total energy of the electron. Now what we have left? We have to relate the potential energy with the kinetic energy. It is so very easy. You can see potential energy is also twice of the numerical value of the kinetic energy. But there is also a difference in their sign. Potential energy is always negative. So potential energy is minus twice of that of kinetic energy. These three relations we can conclude from this idea. So please remember also these three relations for your exam purpose. Okay. Now, just like the radius and the velocities, we will also calculate the energy of a single electron species. So energy of a single electron species will be E equals to 13.6 into Z square divided by N square. And we know the energy, that is total energy of an electron, is always negative. So here E equal to minus 13.6 into atomic number square and divided by orbits numbers square. And remember the unit? Unit is electron volt. So here you have got the energy for a single electron species. Remember also this formula is very very important. So minus 13.6 into Z square by N square electron volt. So now we have come to an end of the energy of electron in any orbit. Now we will just take a look in a different concept of this energy, and that concept I will tell you that is very very important. Nowadays questions are coming, those are actually a bit tricky. So to handle those tricky questions, you need to get that different concepts that I will give you just now, specially related to the NEET and AIIMS question paper. So let's do it. So here are the three terms. One is ionization energy, that probably you all know. Another is separation energy, and the third one is excitation energy. And nowadays I have seen all these three terms in your question paper. So let us take a look over all these three types of energy, and please don't confuse with one another. All these three energies are used to remove an electron from its orbit. So all these three energies are positive in nature. Now where is the difference? Now ionization energy is the minimum amount of energy required to liberate or remove an electron electron from its ground state, that is N1 equal to 1 and N2 must be infinity because the electron is totally removed from its ground state. Ionization energy is the minimum amount of energy required to remove or liberate an electron, that is N2 must be infinity, from the ground state, that is N1 is 1, and the separation energy is similar to that of ionization energy. But the difference is here electron is not removed from the ground state, rather it is removed from any one of the excited state. So here for separation energy the N1 value will be anything except 1. It may be 2, 4, anything, and N2 value is also infinity here. Now the excitation energy, the N1 value is 1 here and N2 value is anything, 2, 3, 4, 5, anything. Okay, now you tell what is excitation energy? Excitation energy is the minimum amount of energy that is required to remove an electron from its ground state to any one of the excited state. Okay, so here are the three terms of energy: ionization energy from ground state to infinity, separation energy to remove an electron from any one of the excited state, not the ground state, to infinity, and excitation energy is the minimum amount of energy to remove an electron or to change an electron from its ground state to any one of the excited state. Okay, so please remember these three terms of energy, and later on I will show you that how these terms are involved in your question paper. So today's lecture is up to this. Now I will tell you all the numericals from this part you will be getting in a separate video. Okay, all the previous year's solved questions and everything you will get in my next lecture. You can check the I button and the description below for other lectures of the atomic structure. Please stay connected and don't forget to subscribe and like my. Stay tuned for next lectures. Thank you all. Stay blessed and stay cool. Bye bye.